All right, ladies and gentlemen, we're going to look at kinetics. This is going to be a little bit of a difficult chapter. You guys should be able to do it. The concepts are actually fairly easy. It's the applications of the concepts that can be kind of complicated. So, first question is, what is kinetics? Let me get my pen going. So, kinetics, as you can see here, I changed my pen color to blue. It's basically the study of the rate of reactions. So, basically, how fast the cellular reactions are occurring. And this is what kinetics is. And basically, we're looking at how long it would take to create a compound or remove a compound. And this is going to be important because these two things, meaning is important to know, hey, how long do we have to wait to make something or to remove something? Sometimes removal is key. So rate is important in this. And rate, we're going to talk about in a minute. And then this is important in medical and environmental fields. How long will something last in the environment? Or how medicine will last in the body to be effective before it loses potency or gets drawn out of the system. So this is all what kinetics is. It incorporates a whole lot of fields, and that's people actually study kinetics. And we're going to look at just the simple stuff, simple reactions, simple stuff. So for most reactions, the rate is the amount of substance changes as a function of time. So we're looking at amount of substance. Usually it's in grams or moles per liter, concentration, amount. So we're looking at mass, or the moles per liter, or moles, or grams as a substance, as amount of substance. So we're looking at a function of time. So usually we look at big M over seconds. This triangle is change. That's all that means. And this screws everybody up. And no matter how much I say, everybody's like, oh, I got two variables. No, this is one. This means change. You're looking at differences of things. And usually you start at 0 or end at 0. So this is the change in concentration of X, and delta T is the change in time. So the rate we're looking at is this equation. Next lecture, we're going to deal with that in a little bit more detail. But let's look at reaction schematics. And this is an ugly picture. Ugly, ugly, ugly. But we've got A plus B. And this is actually, if we go up, this is energy. And this is total energy that the system has. So this is system energy. And so what happens, in this case, A plus B, we need to add energy to here. That from here to here is called activation energy. And then we have an intermediate at the top, and then quickly goes to C plus D. And if this is amount of energy that is absorbed or released. Now, if this is higher than this, energy is absorbed, and it's a, what type of reaction? And now I got this mixed up. This reaction absorbs energy, well, endothermic. Change in energy is positive, and exothermic is when it's down here, and it's the change in energy is negative. Because remember, change is final minus initial. So if it ends down here, the final is lower than the initial, so therefore it's negative. That means energy is released. Now, when we're looking at this, several factors that are involved affecting rate. We're going to talk about the first three today. Concentration is the next couple of lectures because it gets more complicated. So we have catalysts and inhibitors. We'll look at those in a minute. Surface area affects the rate, temperature affects the rate, and then concentration of the compounds. So let's look at catalysts. Catalysts and inhibitors are very similar. It increases the kinetic of the reactions, it makes it go faster, but it's not consumed. So, and the inhibitor is a compound that decreases the rate of reaction, but it's not consumed. And guess what? We're talking about things that are not used, they're just there. It can make things go faster or make things go slower by changing the activation energy. It won't be present in an equation describing the rate of the reaction, but when we add it, if we have to add a catalyst or an inhibitor, it is listed up here. So this is my catalyst. So it's always listed on the top of the arrow or below, but it is not in the actual equation because we don't want to put it in the equation to say, hey, look, it's undergoing a reaction. E doesn't get transformed, it just stays there. They will interact with the reagent but not react, and that is the key. So when we look at reaction schematics, if we add a catalyst, catalysts lower the activation energy. So I hit the blue line is my catalyst with catalyst present. And when we lower the activation energy, that means more atoms are up there. This energy reacts faster and we produce more C and D. Let me change my pen color to, let's see, magenta. If we're looking at an inhibitor, this is an inhibitor. It raises activation energy. Therefore, it's going to be slow. Now, everybody's looking, what do you mean by that? So let me come down here. Let me show you something. If we have temperature and the number of molecules, at a certain temperature, we got the maximum number of molecules here. We got some slower and some faster. If we increase the temperature, we're shifting this over, so the average is here. Now, let me redraw this in blue. If I have my number of molecules for temperature, this is the number of atoms or molecules versus temperature. If my activation energy is here, it's going to take a while to use up some of this because you're going to end up taking some of this away. The curve's going to shift over. You may have some left. Now, if I lower the activation energy to here, got a lot more that's able to react with the substances to react. And that's what we want to do with the activation energy. It's move it down here below the average temperature. So a lot more molecules have the energy to react. If it's up here, it doesn't. And so it's all based on numbers and probability. And this is what kinetics can get into. So this is what happens when we add a catalyst. It lowers the activation energy, moves this line over to here, and now we have a lot more molecules actually doing the reaction. Next is surface area. Surface area on the reagent will react the reaction rate. All reactions or should I say, most reactions occur at the surface of a solid or a liquid. So then if you increase the surface area, you're going to increase the rate of reaction. So which has more surface area? You got 1 cube with a dimension of 1 centimeter cubed, or 100 cubes with a dimension of 1 millimeter. And it's actually going to be this one. It's going to be faster. And I'll show this in class because I'm running out of time on my lecture. Let's go through one more. A couple more things. Temperature. Temperature of the system will affect the reaction. Raising the temperature will decrease the amount of activation energy needed. But in some reactions, raising the temperature slow it down. So if we look at this, on this reaction schematic, if we increase the reaction rate, the temperature, instead of being down here, now we're up here, reducing the amount of energy that we need to get to this point. So what we're doing with the catalyst, we're lowering this down, but when we raise the initial temperature, we're raising the whole thing up to here. And that's what I mean by reaction schematics. This is what I mean by looking at temperature, how it affects reactions. Now, if this is an endothermal reaction, this is going to make it harder to come because it doesn't like to. It wants to give up a reaction. So this especially works if the products are basically lower than the initial reagent. Now there is an equation that we're going to work with, and that is this equation. The rate constant is equal to A, the frequency factor, which is a probability factor, E, which is the natural exponent, raised to the minus activation energy, over RT, and that R is the gas constant, T is the temperature. And I'll have a problem set for you guys to work on this, and I'll give you the rest of the slide later. That's my cat telling me to hurry up and finish, so I will. Thank you guys. Have a good day.